Hey everyone, thanks for joining me today. My name is Laly Bar-Ilan. I'm Chief Scientist at bit.cloud, and today I'm going to show you how teaching AI to work with components can help you build features faster, reuse more of your own code, and stay in control of your codebase. By the end of this talk, you'll learn how to shift from using code generation tools that produce isolated code snippets to using AI with an architecture-first mindset. This will help you not only build faster, but also keep your codebase maintainable, scalable, and understandable over time. Because if you think about it, software development has never been about writing lines of code. Writing lines of code is just a means to an end, which is creating digital products and features. However, if you look at today's code assistants like Copilot or Cursor, which I'm sure a lot of you are using, they don't see this big picture yet. They do an impressive job creating code snippets and files, but they don't see the products, the features, and the architecture we're actually trying to build. So today, I'll show you how teaching AI to think in components lets it move beyond code snippets and start building full products and features and platforms with composable architecture principles and reusable components. I'll show you why components are the ideal building blocks for a common language between developers, data scientists, non-technical stakeholders, and, of course, AI. And why this language can help keep us humans in the loop as AI continues to advance. Let's dig in. We'll start with a quick journey, surveying how our communication with machines has evolved over time, and why speaking in components is just the natural next phase. In the beginning were zeros and ones, right? In the 1940s, the first programmers had punch cards, where each hole in the card physically controlled a machine. No abstractions, no shortcuts. You are literally speaking the machine's language, one painful bit at a time. Then, in the 1950s, came assembly languages, with commands like move, add, or jump. Still close to the hardware, but now you could use symbolic instructions instead of remembering endless binary codes. So this was a small step toward human readability. The real jump, though, came with high-level procedural languages in the late 50s, like Fortran and COBOL, and in the 70s when C was invented. These languages introduced structured logic, loops and conditionals and functions, and they were the first compiled languages. The code you wrote was already semi-human, and the compiler translated it to machine code. Then in the 80s and 90s, we started using object-oriented programming with C++ and Java. These languages really nailed how we see the world as humans, because the code was finally organized around objects that modeled real-world entities, not just procedures and instructions. The turn of the century, the mid-90s to early 2000s, saw the rise of scripting languages like JavaScript, Python, and PHP. So these languages not only added another level of abstraction, but also shifted programming even closer to natural language. Not only that, but they encapsulated many tiring technicalities like memory allocation and manual compilation. These freed us to focus more on logic and outcomes rather than infrastructure, and this is an important shift. Remember it for later. And in the past couple of years, we've entered a new frontier, which is AI-assisted coding. Now we have low-code and no-code platforms, and we have code assistants for code generation. These aren't just new tools. They represent a new kind of language. It's not exactly natural language, and it's not also code in the traditional sense. It's more like a dialect of English with domain-specific jargon. Let's call it a semi-natural language. In just a few decades, we've moved from speaking directly to the hardware to conveying the abstract concepts of human intent. So if you think about it, the history of programming is actually the history of making machines fluent in human language. So what do components have to do with it? This evolution that we just saw has two main characteristics. One, it moves away from the hardware toward human language and conceptual systems. Two, the building blocks of communication between humans and machines gradually shifted to bigger and more complex building blocks. Just like you can see with the Russian dolls here. So these bigger and more complex building blocks, they encapsulate more and more of the technical complexity, allowing us to focus on the architecture and the business and product intent rather than technicalities. In the earliest days, a single instruction might simply move a value into a register, a tiny mechanical action. Later, a building block might represent something bigger, like a mathematical operation or an algorithm. And as abstraction grew, our building blocks expanded. They became user accounts and shopping carts and payment flows. They became real-world entities and actions, wrapped up neatly in code. And as abstraction grows, so do the meaning-bearing units we build with. We no longer move single bytes, we move products and features. And these are best represented by components. Let's dig into that a little bit and see what components are. Essentially, components are independent software entities, each representing a single business or product functionality. They're like packages or mini repositories designed to be shared and reused across projects. You probably know components from front-end. Most developers are at least familiar with React components like headers and buttons and web pages. But we at Bit use components to model our entire codebase, both front-end and back-end. So we also represent each entity, each database handler, each algorithm, and each microservice as a component that everyone can access and reuse. But one of the most important things about components is that they encapsulate all the gory technical complexity. First of all, the business logic itself, the implementation. Then things like tests and configurations and version control, all the things that you don't really need to know in order to use a component. It's like you don't have to know what Lego bricks look like on the inside in order to connect them with other Lego bricks. You just need to know what they look like on the outside. So I imagine components like an iceberg, where you only see the tip, which in our case is the component's API and docs. But that's really all you or the AI need to know in order to use them. Having a product meaning and a human-readable interface and hidden implementation makes components the ultimate building blocks for a common language, a lingua franca, if you will, that can connect both non-technical stakeholders and AI to what we do as developers. Moreover, as developers, we can be less and less bothered by implementation and move more and more towards higher level product and architecture definitions. So components are the words in that language of product and business meaning. But like any language, there's also syntax, a set of rules that defines how those words fit together. In this case, that syntax is the component dependency graph. Here's an example. You can see that each node on the graph is a front-end or back-end component, and each edge is a dependency relation. This graph represents an architecture of the entire codebase. So you can see, for example, that header depends on logo, avatar, and navigation menu, and that in turn, navigation menu is using search box, which uses button and search service, and so on. But this graph actually represents something much more. It's a live map of the entire business and product functionality in the organization. This has a few crucial implications. This map, first of all, is visible and clear to everyone in the organization, including non-technical stakeholders and upper management. Second, it promotes reuse. When we want to create new functionality, we first search for it on the existing graph, and then we create it only if it doesn't already exist. So if we see, for example, that menu already exists, we'll use it instead of creating a new one. This keeps our codebase lean and healthy and prevents it from inflating. But most importantly, this map can be taught to AI and help it become an amazing software architect. Think about it. When a human developer and AI look at code, they both seemingly see the same thing, lines of code. But there's a significant difference. When AI looks at our code, it only sees sequences of tokens. What are tokens? Operators, names of functions, classes, and variables, reserved words, all the ifs and elses. And this is comparable to viewing a topographical map. You get an exact view of the terrain, but you don't see the functional meaning and boundaries that we see as humans. When we look at the code, we see it more like a political map. We see the functional boundaries between products and features. We see the components that make up our code, and we see their connections. And this is what we want to teach AI to do. We want to teach AI to work with components for a few reasons. First of all, tokens have a very small syntax level meaning, while components have product or business meaning. Components have clear APIs that allow them to be easily composed with each other, which turns the task we give AI from generation with tokens to composition with components. Instead of generating lines of code from scratch, it searches for existing components that can be reused and composes them together, which is a much easier task than generating from scratch. Third, components encapsulate their implementation. So they both protect the organization's IP because they don't expose the implementation to the model, and they don't burden the model with unnecessary details. They provide only the exact context the model needs without burdening it with implementation noise. Just like what I said about Lego bricks a few slides ago. In order to put them together, you don't need to know what they look like on the inside. Now, providing AI with components and their relations through the component graph means that the AI no longer needs to infer the business or product functionality from sequences of tokens. And it also doesn't need to infer the relations between parts of the code anymore from import statements scattered across files and repositories. Both the product and business meaning and the relations are provided to the model explicitly. But if we want to be accurate, what we're actually doing is we use a hybrid approach to code generation. It's both top-down, architecture first, and bottom-up, which is generating tokens. How exactly does it work? It all begins with a user prompt. So the user prompts the model to create a product or feature, build me a shopping cart or a website for blogging or an authentication service. So we start top-down. The model creates the architecture of components that make up this new feature. It then proceeds to search existing components it can reuse in this architecture, and it uses whatever relevant components it found. Then we move to the bottom-up part, which is composed of three elements. One, making modifications in existing components, if necessary. Second, generating glue code for using these components. And third, generating new components for the relevant functionality that doesn't exist yet in the component graph. So it also generates tokens, but it generates them into actual components and not just snippets. Then finally, after human review and approval, all the changes and new components are immediately integrated into the component graph and are reusable for everyone, both humans and AI. What does it actually look like on our platform? So at the top left, you can see the user's prompt, build a news platform. Then our model, called Hope AI, suggests the architecture. Here, for example, you can see it's suggesting a few scopes: design, news platform, and articles. And you can also see that the components inside them, some are new, but some are reused and some are modified. Finally, on the right, you can see what it looks like in production after the components have been created and approved by the developer and deployed. So, what does this shift actually mean for developers? Let's start with speed. Many of us, probably most of us, are already expected to deliver at AI speed. This shift is happening whether we're ready for it or not. But working with components makes that speed manageable. First of all, you spend less time on low-level implementation and more time on high-level architecture, which accelerates delivery. Second, you ship faster because you reuse and compose rather than code from scratch. Third, new and modified components, since they're automatically integrated into the graph and instantly reusable, over time, you need to generate less and less components. The more components you have, the more you can reuse, the less you need to create. And finally, components are runnable and testable, so you can validate their functionality and their impact on the rest of the graph before they're deployed. This is a big difference to the systems that exist today. The second implication is having maintainable code bases. So building with components doesn't just make us faster. It keeps our code bases lean, understandable, and scalable. How? First, as I said before, the component graph is a live map of all the business and product functionality in the organization. So all the existing components are visible to everyone. And you and the AI can always know what you can reuse. Second, representing the entire codebase as one graph means that changes are made at the component level and not scattered across files and separate repositories. This makes it easy for both humans and AI to understand and maintain. Third, by reusing components, we avoid inflating our codebases with duplicate functionality. Today, two developers sitting in the same room can ask the model to generate the exact same functionality, let's say a button, and the model will happily create both instances. Now think about what happens in a big company over time. How much duplicate code is created, and how much chaos it can create at scale. The third thing I want to talk about is collaboration. So that's another interesting aspect in that shift. It doesn't just affect developers. It transforms collaboration across the entire organization. At the center, we can find the component graph as a basis for collaboration. It's visible to everyone, even if not everyone goes into the implementation details or can understand them. Then, in the circle closest to it, we have developers and AI who can compose features and guide architecture and review outputs. The next circle includes non-technical or less technical stakeholders that are still involved in the development process. The product managers and designers who can now see, understand, and iterate on the component graph. How come? Because, first of all, people don't have to be highly technical to understand component APIs and docs. Second, components have version control, so now product and design can actually make changes and open pull requests and review and approve components. This means that they are now part of the development loop, much more than before, which makes dev cycles a lot faster and more efficient. Then, in the outermost circles, we have marketing, sales, business, and leadership teams who, for the first time, gain visibility into system structure and feature flow. So they can now understand how the product is actually evolving in real time. Basically, this is what happens when development becomes a shared language rather than a siloed activity. And finally, as we assign more and more development tasks to AI, it's important to think about how to keep humans in the loop in the long run. This is another advantage of components as a shared language for a few reasons. First, using components, we have a shared entity to collaborate on and improve over time. AI can propose improvements which humans can understand and validate or fine-tune. It's so much easier to read component documentation and tests than going over all the lines of code in a snippet. And when human developers change individual components, it's easier for the AI to understand these changes, and not only that, it can also understand their impact on the entire graph. Second, when we build with components, we augment our codebase carefully instead of just letting AI generate endless amounts of duplicate code. This keeps our codebases lean and understandable to humans in the long run. Third, human control over AI crucially depends on the permissions we give it, what it can access, what it can decide. A modular component-based approach ensures granular permissions. Instead of letting AI act across a monolithic system, each component is isolated. So if something behaves unpredictably, it can be reviewed or modified or replaced without risking the entire system. In short, composable AI means controllable AI. Critical decisions stay human-controlled, AI can't overstep, and systems stay safe and visible and scalable. So through components, humans and AI are finally speaking the same language, the language of product functionality, architecture, and intent. This is how we build faster and smarter and how we keep humans in the loop. Because let's face it, Git blame only tells half the story now, doesn't it? So thank you. Come check us out at BitCloud and connect with me on LinkedIn. My name is Laly Bar-Ilan. I'd love to hear your thoughts. And of course, if you have any questions, I'd love to answer. So hope to hear from you and hope you enjoy the rest of the conference.